Hello everyone, welcome back to Physics 331. What I'd like to do today is to continue our discussion of transmission lines. Specifically, I want to achieve two things. The first is I want to understand when some of these transmission line effects that we've been discussing, when are they important and when can they be ignored? So for example, in a course like Physics 231, whether you did the lab in person or online, when we were analyzing or measuring circuits, we never really worried about the fact that the voltage or the current along a pair of conductors in your circuit may not be uniform. They may be varying along the length of those conductors. And so why could we get away with that kind of assumption, and when do we have to be more careful? And then the second thing that I want to discuss is what the effective input impedance of a length of transmission line is. And so we'll do a calculation to see if we can determine that. To achieve these two goals, I'd like to just summarize a couple of the useful results that we've gotten from some of the previous videos. Let me just remind you of the geometry. We have a length of transmission line of length L, and there's a z-axis along the length of the transmission line, and we've chosen 0 to be at the right hand side of the transmission line, and at the left end we've set z equal to minus L. And so with that geometry, we went ahead and we calculated how the So we assumed that we had sinusoidal signals on our transmission line, and capital V represents the amplitude of those sinusoidal oscillations, and we calculated how that amplitude varies along the length of the transmission line. And so here's the expression. And we also calculated how the current amplitude varied along the length of the transmission line, and the result is here. There's a couple of parameters in these expressions. Remember, V plus corresponds to the V plus coefficient corresponds to a wave traveling along plus Z, and the V minus to a wave traveling along the negative Z direction. The quantity beta was the wave number, 2 pi over lambda, and it was given by omega, the angular frequency, times the square root of the inductance per unit length times the capacitance per unit length. In the current amplitude expression, we had the characteristic impedance Z0, and that was given by the square root of the inductance per unit length divided by the capacitance per unit length. Okay, good. So let's start with our first objective. And really what we're trying to do is answer the question, why don't we worry about transmission line effects in a course like Physics 231? Okay, where you design a bunch of useful circuits that can do filters, amplifiers, resonators, things like that. So let's start with thinking about some of the transmission lines that we might actually use. So the coaxial cables we use in the lab are called RG58, and they're designed such that the capacitance per unit length is about 80 picofarads per meter, and the inductance per unit length is about 0.20 microhenries per meter. Okay. So if you think back to 231, we might not have used coaxial cables too much, but we would have had, say, banana cables, and those banana cables you had one connected, say, to the positive output of the function generator and one to the negative output or the ground. And so they are a length of parallel conductors, and they act as a transmission line as well. And so they'd have their own effective capacitance and inductance per unit length. But anyways, let's use these numbers for the coaxial cable because they're well defined. So if you were to go and then calculate the characteristic impedance of such a cable, it would be the ratio of the inductance of capacitance and square root. And if you put in these numbers, that would come out to be about 50 ohms. Okay, so the other thing we want to do is we want to calculate the value of beta. And so beta is equal to omega times the square root of the inductance per unit length times capacitance per unit length. So what we have to do is we have to assume a value for the frequency in order to complete this calculation. And in Physics 231, we might have worked in the frequency range somewhere between typically a kilohertz and maybe 100 kilohertz. And so as a mid-range frequency, let's just take the frequency to be 10 kilohertz. So let's take omega equal to 2 pi times 10 kilohertz, just for example. You could choose a slightly different value, and it wouldn't make a difference to what we're going to do. So in that case, using the capacitance and inductance that we have above, and using omega as 2 pi times 10 kilohertz, beta comes out to be around 2.5 times 10 to the minus 4, and the units are inverse meters. The important thing here is not really the actual numerical value of beta, just that it's a small number. It's a number, say, that's much less than 1. Okay, so this is something like, 1 over, or 4 over 10,000 or something like that. Okay, so that means this factor of e to the plus minus j beta z using Euler's formula is equal to cosine beta z plus minus j sine beta z. So we know beta is very small, and if we think of z, say the typical length of conductors in Physics 231 lab, those conductors are going to be, say, much less than a meter long. So as long as z is not really, really huge, we could say that for z kind of less than or on the order of a meter, then beta times z is a small number, and the cosine of a small number is 1, and the sine of a small number is 0, and to a very good approximation, this complex exponential is going to be 1 plus or minus j times 0, or it's about equal to 1. So therefore, when you go and calculate how the amplitude of the voltage varies along the length of such a transmission line, say a 1 meter length when the frequency is 10 kilohertz, that's going to be equal to the V plus coefficient e to the minus j beta z. But we've just argued that the e plus minus j beta z is just 1, so this is going to be 1. And then it's going to be plus v minus e to the plus j beta z. But again, that exponential is just going to be 1. And we get that this is just equal to some constant value of these coefficients v plus plus v minus. The important thing is that this is just a constant. There is no variation of the voltage amplitude along the length of the transmission line. Put another way, in other words, the voltage amplitude, which we've been writing as a function of Z, is independent of Z. And so you could do the same thing for the current amplitude, and you would get, again, that the amplitude of the current is independent of Z. I mean, you could go ahead and do that. What I think you'll get is that the current amplitude is 1 over the characteristic impedance Z0 times V plus minus V minus. And so there's no Z dependence at all. Okay, so let's think about this a little bit more. We have a value for beta, right? 2.5 times 10 to the minus 4. Remember, in the previous video, we came up with a physical interpretation of beta. And that physical interpretation was that beta was the wave number. So beta was equal to 2 pi over lambda. Or, of course, that means lambda is 2 pi over beta, which is 2 pi, and beta is omega square root inductance per unit times capacitance per unit length. And if we stick with our numbers for omega is 2 pi times 10 kilohertz, and the values of the inductance and capacitance per unit length for the RG58 cable, we would calculate lambda is equal to 25 kilometers. So at these low frequencies of 10 kilohertz, the wavelength of the signals is massive. Is much longer than any of the cables that you would be using in a typical circuit. So what we conclude then is that this wavelength is much longer, or let's say much greater than the length of any of the conductors, or if you like, transmission lines used in a PHYS 231 circuit. So the summary is the following. When the length of your transmission line is much less than the wavelength of the signals propagating in your circuit, the voltage and current is uniform, independent of Z, along the transmission line. And the transmission line effects can be ignored. Okay, so let's think of a counterexample. So if, on the other hand, we use omega is 2 pi times, let's say, 3 gigahertz. So a much higher frequency. So we were thinking of 10 kilohertz before, which is like 10 to the 4 hertz. 3 gigahertz is like 3 times 10 to the 9. So we've gone up by, more than 5 orders of magnitude in frequency. Okay. And so let's assume we're still using the same RG58 cable, so we're keeping the inductance per unit length and the capacitance per unit length the same. So in this case, if we were then to go calculate beta, which is omega times the square root of the inductance per unit length times the capacitance per unit length, the only thing that changes is obviously just the value of the frequency. If we put these numbers in, we'll get about 75. And again, the units are inverse meters. And then if we go and calculate the wavelength, that's going to be 1 over, it's going to be 2 pi over beta. And beta is omega over square root of L times C. And so that's going to be around 8 centimeters. And so now the wavelength is shorter, or it's shorter than typical wires that you might have in your circuit, or at least it's on the same order of, it has the same order of length of any transmission lines or conductors you're using to connect the components of your circuits. Okay, so if we then go think about the voltage amplitude as a function of Z, it's V plus e to the minus j beta Z plus V minus e to the plus j beta Z. Beta is 75. And so as we change Z from, say, 0 to 0.01, 0.02, 0.03, 0.04, as we approach like the size of the wavelength, for each value of Z, we're going to get a completely different value of the voltage amplitude. So in this case, the voltage amplitude does vary as we change position along the length of the transmission line. In other words, as we change Z. So I think then, to summarize this finding, we could say that when the length of your transmission line is greater than or similar to the wavelength of the signals propagating in your circuit, we cannot ignore transmission line's effects. In fact, the transmission line effects are important. So I think some of the things that we've been talking about are important when you are either working with very high frequency signals, which occurs when you're, say, in the microwave or RF frequency range. So there are a couple projects that we are doing in the lab that kind of approach these limits, and so that is the wireless power transfer experiment is operating at several megahertz, and then the split ring resonator experiment is at several hundred megahertz. And so in these projects, one has to be worried about, well, maybe not a little bit, one has to really consider transmission line effects. Okay, good. I guess the other case where these are important is you could go to low frequency, but also work with transmission lines that are very long. So, for example, the hydroelectric poles that deliver power to our homes use kilometers of length of parallel conductors strung up on these poles or buried underground. And although the frequency is very low, 60 hertz, if you have hundreds of kilometers of wires, then there can be transmission line effects to take into account. All right. So that's the first thing that I wanted to discuss. The second thing that I wanted to discuss is the input impedance of a length of transmission line. And I'm going to add something to this. When it is terminated with a load impedance ZL. Okay, and so I'm going to draw this picture again. So we've got a length of transmission line. I'm going to call this Z equals minus L like we've been doing, and here's Z equals 0. And so when I say input impedance, I want to know what the impedance is when we're looking into this transmission line and the other end, the opposite end, is terminated with a load impedance. So that just means we have an impedance ZL connected across the pair of transmission lines. And so across the pair of conductors, I should say. So we could pick some point, and so let's say this is the point Z. And so over here we're going to have some current amplitude I of Z, and there's going to be a voltage amplitude V of Z. And so down here at Z equals 0, we have the voltage across our load impedance, which I'll denote VL, and so that's also equal to V when Z equals 0. And then we'll have a current in our load impedance IL, and that's just equal to I when Z equals 0. Okay, so we're going to go back and we're going to use some of the results that we've already been using. So let's say that we know the following. We know the Z dependence of the voltage amplitude and current amplitude, and they're given by these expressions, which are now beginning to be a little familiar. V plus, that's in the current, that's a minus sign, so minus V minus e to the plus j beta Z. And what we know is that the characteristic impedance Z naught is 1 over square root of L divided by C. And something we haven't used today, but we worked out in the last video, was that there was a relationship between the coefficients V plus and V minus. They were related by, remember, a reflection coefficient, which we denoted by capital gamma. And capital gamma was determined by the load impedance minus the characteristic impedance divided by the load impedance plus the characteristic impedance. And so let's just remind ourselves that this is our reflection coefficient. Okay, good. So what we're going to do is we're going to write down the value of the impedance of the transmission line at an arbitrary position Z. And so we have expressions for the voltage amplitude and current amplitude, and by definition, impedance is given by the ratio of the voltage divided by the current. And so what we can say is at an arbitrary position Z, so some Z between minus L, the length of the transmission line, and 0, the impedance is given by, so Z at some arbitrary position Z. So capital Z is the impedance, little z is position, and so that's going to be the voltage divided by the current. Okay, so that's just going to be V plus e to the minus j beta Z plus V minus e to the plus j beta Z is the voltage amplitude, and then divide by current is 1 over Z naught V plus e to the minus j beta Z minus V minus e to the plus j beta Z. Okay, so all I'm going to do is I'm going to rearrange a little bit. I'm going to put the Z naught in the numerator, and I'm going to replace V minus with gamma times V plus. Okay, so that was the relationship that we had worked out before. So we can write V minus in terms of the reflection coefficient and the V plus coefficient. If we do that, then each term in the numerator and the denominator will have a V plus that we can factor out. Okay, so doing all of that, the impedance at position Z is going to be equal to Z naught V plus. In the numerator, we'll have e to the minus j beta z, and we'll have plus e to the plus j beta z. And in the denominator, we'll have a v plus, and we'll have, oh, sorry, I forgot something here. Let me go back to the numerator. We have to put in for v minus gamma times v plus. We factor out the v plus, but we still have a gamma and ej beta z. Okay, and then the denominator, e to the minus j beta z, and then it's minus gamma e to the plus j beta z. Okay, and so of course the v plus cancels out. And so that's convenient because now we have this impedance just written in terms of things we know. We know the characteristic impedance, that's just determined by the geometry of the transmission line. And gamma we can calculate, it's just the characteristic impedance. It's determined from the characteristic impedance as well as the impedance at the terminating the end of the transmission line, and so presumably we know that value. So in fact, what we can do is we can put in that expression for gamma, and I'm going to calculate, I'll just write this as the impedance at position Z divided by Z naught, and that's going to be equal to e to the minus j beta z plus, and then our reflection coefficient is ZL minus Z naught over ZL plus Z naught, and then e to the plus j beta z. And then the denominator looks the same, except there's a minus sign between the two terms. Okay, so we're just now going to try to clean this up a little bit. So let's multiply the top and bottom by ZL plus Z naught. We're just going to try to get rid of the fraction that exists currently in the numerator and the denominator. So if we do that, we'll get the impedance divided by the characteristic impedance is going to be, let's see, ZL plus Z naught e to the minus j beta z plus ZL minus Z naught e to the plus j beta z. And then again, the denominator looks the same other than the sign between the two terms. So we get a minus sign here. Okay, good. So what we'll do is now we have things kind of collected in terms of like things multiplying the same exponential. What I'd like to do is to collect terms that have ZL and terms that have Z naught. So in the numerator, we have ZL multiplying e to the, let's see, we have a e to the plus j beta z, and then we have a plus e to the minus j beta z. And then for the Z naught, what do we have? We have a minus e to the plus j beta z, and then we have a plus e to the minus j beta z. Okay, and then in the denominator, we'll put a ZL here, and we have a minus e to the plus j beta z and a plus e to the minus j beta z. And then we have a plus z0. And we have plus e to the j beta z plus e to the minus j beta z. Okay. So it looks messy at the moment until we can clean this up a little bit. We could say, recall the following identities. We had Euler's equation for writing a complex number, complex exponential in terms of sine plus j cos plus j sine. So we could equivalently write the trig functions in terms of complex exponentials, and cosine of x is equal to e to the jx plus e to the minus jx divided by 2, and sine of x is equal to e to the jx minus e to the minus jx over 2j. And so what that means is if we look at these terms that are in the brackets here, we could recognize a couple of things. We have e to the j beta z plus e to the minus j beta z. That's equivalent to 2 cos beta z. Okay, and then over here we have e to the j beta z minus e to the j beta z plus e to the minus j beta z. So that looks like minus 2j sine beta z. Okay, so let's re-express this impedance that we're calculating in terms of these trig functions. Okay, in the numerator, we're going to have ZL times 2 cos beta z. So I think we have 2ZL cos beta z. And then we're going to have minus 2jz0 sine beta z. So this is, I think, is minus 2jz0 sine beta z. And then in the denominator, let's write the cosine term first. 2z0 cos beta z. And then we have minus 2jzl sine beta z. Okay, good. So there's lots of factors of 2 that we can cancel. And the other thing we can do is we could divide top and bottom. Here, I'll write it in words first. So let's divide top and bottom by cos beta z. Doing that, our impedance divided by the characteristics impedance is going to be ZL, and we divide by the cosine, so that's gone, minus JZ0, and then we'll have sine beta z divided by cos beta z, which is just tan beta z. And in the denominator, it's the same thing except that the order of the Z0 and the ZL are switched. So I think that should be right. Okay. So that's good. That's that's kind of a result for the impedance at an arbitrary position of Z. But remember, our Z range is from minus L to 0. Right? If we go back, way back, and look at this picture, what we're going to try to do is to calculate the Z in when Z equals minus L. Okay, so we're now in a position to do this. Therefore, Z in, looking into the transmission line, at position Z equals minus L is, well, all we're going to do is we're going to take the Z in the tan beta Z and put in minus L, but the tan of minus X is equal to minus tan X. So tan of minus beta L is equal to minus tan beta L, and so that minus sign is going to cancel with the minus signs that we already have in our expression, and the result is that the impedance at position minus L, which is defined to be our input impedance, is going to be, we have to multiply by the Z0 that we've been carrying around in the denominator on the left hand side. So we'll have an overall Z0, and then we'll have a ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. And so this is the input impedance of a transmission line of length L terminated by load impedance ZL. So let's just repeat that again. This is the input impedance of a transmission line of length L terminated by an impedance ZL. Okay, good. And so I think that's where I'm going to stop. In the next video, we'll look at some special cases, and then we'll look at why this is a useful thing to know and how it can be used when, for example, trying to design an experiment that operates at frequencies where these effects are important. All right, thank you very much.